Welcome back to our grade 11 maths lessons. I am Miss Awinup, one of your maths teachers. Now you can see on the board, we have a diagram. Now this person is Jule, his name is Jule, okay? And he's trying to move this box across this flat surface here, all right? And this is called displacement, he's applying force. We are going to come back to him in the middle of our lesson, but keep this at the back of your mind. Force and displacement are vectors, all right? Now, what is a scalar? All right, scalar spelled S-C-A-L-A-R, all right? It's a constant or a number with no direction, a number that simply increases in magnitude or size, all right? So, if we're multiplying a vector by a number, what happens to the vector? All right, we'll have to show this on a Cartesian plane. Okay, so once our Cartesian plane is up, let's have a look at a vector. What happens to this vector when we multiply by a scalar or a constant number? Okay, so let's see this vector, let's give it its x and y components, okay? And we're going to put that in a matrix. Let's say this is vector A, all right? So vector A, and its x and y components being 2 and 1, all right? And we are going to multiply this vector by a constant number of 3, okay? So 3 multiplied by vector A, all right? What do we do with 3 and the x and y components? We are going to multiply that constant number by each of the components in the matrix here, okay? So let's rewrite this as 3 times 2, okay, and 1 or 3 times 1, all right? Our result will also be an x and y component of 6 and 3, okay? Now what's going to happen to the vector? Let's draw this into the Cartesian plane and see what happens. So we have an x component of 6 and a y component of 3. So our vector, okay, has increased in size. All right. The direction has not changed, but that vector, which was originally 2, 1, has increased by 3 to 6, 3. Okay. Now, what if we multiply this same vector by a negative number? Okay, a negative number. So let's say negative 1 is multiplied by the vector A. Okay. And the same thing applies. We are going to multiply that constant number by the x and y component of the vector. So negative 1 multiplied by 2 and negative 1 multiplied by 1. The result, okay, so that's negative 2 and negative 1. Now let's show this on the Cartesian plane. Negative 2 and negative 1 would be right here, okay? Now what's happening to the vector now? Because the number or the scalar is negative, that negative direction flips our vector so that now it is going in the opposite direction, okay? So multiplying by a positive scalar or constant, our vector simply increases in size and direction is left as it is. However, if we multiply by a negative scalar or constant, that direction now flips and that vector is still increasing in size, okay? Now this is interesting. Keep this in mind. We are going to go back to our friend Jule, all right? Now what Jule is showing here is scalar products. Now what are scalar products? It's when you multiply two vectors and then it results in a constant number. Now how do you do this? And you may wonder why and where. This little diagram of Jule shows us where that happens when two vectors are multiplied to give us a scalar product. Okay, so we have force and displacement, which are two vectors, and we want to know how much work he has applied to move this box from here to here. So let's redraw this vector, vector A and vector B. There are two ways to finding the work applied. You can go about solving this using geometry, or you can use algebra to find the answer, okay? With geometry, you would need to find this angle here, okay? And work is found by the amount of overlap, or how much space vector A occupies on vector B. So that would be this distance here, okay? Now you can tell vector A or force here is the hypotenuse, and vector B, which is displacement, is the adjacent side. So using this angle here, we would need to use the cosine ratio, okay? Remember, we are multiplying vectors, so the product of vector A and vector B, all right, would be to multiply the magnitude. Remember, we did this in previous lessons. When you have the vector in the two lines here, it indicates magnitude. So the magnitude of A, or length of A, times the length of vector B, and this is multiplied by the cosine of the angle theta, okay? So we're going to put up a Cartesian plane again, and we are going to assign x and y components to the vectors force and displacement. Okay, vector A is equal to 3i plus 3j, and vector B is equal to 6i plus j, all right? Now remember, I and j are unit vectors, so they are equal to 1. So our x and y components are 3 and 3, and for vector B, 6 and j. Let's put this up on our Cartesian plane. We have vector A, which is here, x and y components 3, 3, and vector B, 6 and 1, which would be down here. Okay, so this is vector B, all right? We are going to solve or find the value of work applied. So vector A times vector B is equal to the x component of A times the x component of B, and we add that to the y component of A plus the y component of B, okay? So going back here, we have xy, xy. So A component of x is 3 times 3 plus 6 times 1, okay? 3 times 3 is 9 plus 6 is equal to 15. Now what is 15? 15 is the amount of work used to move that box. So that measurement will be in joules, okay? Sometimes written as Newton meters, all right? Now, that brings us to the end of our lesson. I hope you have learned a bit or something interesting. In our next lesson, we're going to look at other ways that vectors are applied in everyday situations. Okay, join me then.